Hi everybody, welcome at tutorial 8 of our day on extremes and variability. Now we're going to talk about non-stationarity again, but in relation to the extreme value theory. So we talked about non-stationarity and its as a concept in tutorial 6, where we discussed how parameters change over time. But now we're trying to incorporate it with these general extreme value distributions and the application of return values and return periods and seeing how we can compute those based on non-stationarity. That will be the objectives of today. So just a little bit of a recap. Stationarity is that. We announced that to all of you. But what does that exactly mean? Stationarity was the fact or the assumption that we often make that our record stems from one distribution only. And I mean with that one distribution with one fixed set of parameters that doesn't change over time. We have seen that climate change is making that a little bit impossible for us, that actually stationarity is not really a thing most of the time anymore, and that those parameters change over time, so that we need to account for that to really predict, 100-year floods or 100-year droughts or something like that. So how can we incorporate non-stationarity in these extreme event analyses and these frequency analyses? For that, we need to have a good look at the GEV distribution, or I'm taking GEV as an example here. You could, of course, take any other distributions. But here we're going to look at the GEV parameters. So again, just a little bit recap of tutorial 4. And tutorial 3, we had 3 parameters in our GEV, a location parameter, a scale parameter, and a shape parameter. The location parameter tells you where the distribution is located on a scale of all our variables. So if you look at temperature, which temperatures are involved in our distribution. The scale parameter tells you something about how much values are spread around that location parameters. If it's spread a lot, then the scale parameter is high, meaning a wide distribution. And the shape parameter affects the tails. It's often very important for us in these extreme event analyses. And if you have seen, we cannot really distinguish a time component here. There's no t or something that represents time. And that's an issue because, again, stationarity is about changes of parameters over time. So we need something of time to be included to enable to incorporate non-stationarity. So how are we going to do that? How can we make that part of our analysis? Here you see our record of Hoek van Holland that we have shown you in tutorial 6. We see that it increases over time. There seems to be a linear trend in there. You can actually see that linear trend as well in the location parameter itself. If you just have a close look at those numbers, you'll notice that every time about 70 millimeters is added to it over every 30-year period. When you go from 80 to 16, from 16 to about 60, and from 60 to 70, it's often like 70. It's the same stack that's added by every period, linear. So let's assume that our location parameter is having a linear trend on it. How can we incorporate that? So we see here in the first line, again, our GEV distribution without a time component. Here, mu, location parameter, is one fixed number. It's one number that we incorporate into that formula. However, we can, of course, also change that into a relationship. For example, a linear relationship like you see in line 2. Where you have not mu, but mu is dependent on mu1 and mu0, mu1 being the slope, mu0 being the intercept of our linear equation. And there you find time being included. So what we're actually doing is we're writing our new GEV something like this, where, as you can see, the mu is now represented by this full linear equation. Be aware, we now have 4 parameters: scale, shape, mu1 and mu0, the slope and the intercept. This can now incorporate time as well. So you see that we now very quickly already made our GEV distribution into a 4-parameter distribution with time included, to which we can fit our data. We have time, we have our x values. If we fitted that to this GEV distribution, we have 4 parameters now fitted through the methods that we explained in tutorial 5. What are some alternatives for this? Because do we always have to make our GEV distribution linear on the location parameter? Of course not. There are a bunch of things you can do differently to see if that model better fits the data that we have. For example, you can look at different parameters. In tutorial 6, you saw that there were different parameters have different effects on our record. So sometimes we'll see a record where the scale parameter is changing. And then you can find something like this. So here I added a linear trend to the scale parameter. You see now that we have, again, 4 parameters, mu, our shape parameter, so location, shape parameter, and scale 1, scale 2. Scale 1 being the slope, scale 0, or scale 2 being the intercept. So that's one alternative that you can add. The second is that you can fit a different trend. Of course, it doesn't have to be linear. It can also be exponential or any other nonlinear trend that's found there. Here you see that I instead changed the location parameter in an exponential function with a mu1 and mu0 again, now meaning something differently. You can just incorporate that too. You'll get a very different type of model out of it, but it might be better fitted to your data. For example, to the CO2 that you can see here in the graph, which brings me to alternative 3. You don't have to make it dependent on time necessarily. It will always be a time series, but you can also make it, for example, dependent on CO2 levels, where CO2, the level of CO2 is changing, how much change is actually happening. So here you see I linearly equated to CO2, where now time is just being changed. Like in the case of climate change, this is often a very often used one. You can also change it, of course, into temperature, global temperature, and fit it to that. So with all these alternatives and all these options, what is the best fit? What's the best model to use? That's very hard to determine, and there's no one answer to it, of course. Every system is unique, and every system has its own best model. One of the ways, however, that you can assess this question is by using the techniques that we learned in video 6 from tutorial 6, which is those visual, like splitting up the record in different pieces and then trying to fit GV distributions or normal distributions or whatever distribution to each of those small records to assess changes in the parameters. That's a very effective way. However, of course, you have to be a bit aware that sometimes these parameters these records can then be very small, and then errors can emerge from it. Another way, a statistical way in doing it, is for each model to compute the EIC value, which is a standard statistical test to assess how well a model fits its data. The lowest value is always the best model. So you can run a bunch of models in your whatever programming language you're using, and then assess whether which model has the lowest value. In general, for any of these topics, it's very good to be aware that you need to use common sense. If something is just really weird, for example, a very steep exponential function, and it's probably not very likely that these things are going to work, especially when you think about future projections. You can fit something very well to past data, but it doesn't necessarily mean that the future is going to be the same. So you need to be very much aware of that. Using, for example, a different dependency can help with that. Then finally, how can we compute return levels and return periods from this non-stationarity framework, right? One thing that you cannot do is make the return plots that we did before with that straight line and a log scale. Why? Because now our return values and return periods are dependent on time, meaning that for each year, in this case, because we use that location parameter dependent on time, now each year has a slightly different X-year event component to it, so a different return level and a different return period. So instead of having one such line, we would have 100 lines if our record is 100 years long, and that doesn't really make for nice graphs. So what we do differently is we compute these effective return levels, and we can plot them something like this. So here you see just our normal record, the record that you have seen before with sea level height, and then instead of computing all the return periods and all the return values, we just compute the return values of one return period for each year instead. So in this case, we have the return periods for the 100-year flood in Hoek van Holland. And then for each separate year, you see that you get this red straight line then. So the return, since it's based on a linear relationship with the location parameter, we see that the 100-year flood is linearly changing over time. We also plotted here the stationary 100-year flood, so you can sort of see the difference between the two. And that makes a very interesting set of models, right, if you compare the two. For one, if we had run a stationary analysis, we would have thought that very recently floods became much more extreme because all of a sudden we see much more 100-year floods. However, if you look at the non-stationary analysis, you see actually that in recent times, the values haven't been that bad. That partially has to do with, I think, a small decrease of linear trend in the end of our record. However, it can also mean that just again, recently we haven't seen many extreme events, which might mean that there's much more that we have to prepare for. And that brings me to our last tutorial 9, where we're going to talk about thresholds and how to incorporate these types of analysis in an actual practical manner. Thank you for listening.